let me actually repeat this again. So the regular expressions, we can define the regular expression recursively using this, definition. Okay, let's see. Okay. Yeah, using the definition. It's called recursive definition, just like the regular language. Okay, so the set of regular expressions can be defined as this. First, you can actually build the regular expressions, set of regular expression that way. First part is the basic clause. We actually view the phi, epsilon, and the x are regular expression corresponding to the phi is basically means it's an empty set, and the epsilon basically means it's an empty string. So that's a difference. That's the phi means basically means a set. It's an empty set, and the epsilon basically means the empty string. And x, if x is any actual element in sigma. Okay, so that's the set of alphabet we define, because when we define the finite automata, we always actually define a string on the alphabet epsilon, which is a finite set. So suppose x is any element in sigma, and then we basically say, phi sigma and any x in sigma are regular expressions corresponding to the language phi, epsilon, and x. So that's a regular language. In these, it's a regular expression. So phi is a regular expression in regular language phi. Epsilon is a regular expression in the regular language which contains only the empty string epsilon. And x is a regular expression in the set which contains only one element, that's x. Okay, so remember the difference. Epsilon is an element, x is also an element. It's a, and so, but this is a set. Okay, so epsilon is a regular expression in these in this regular language, which contains only the epsilon, the empty string, and x is the regular expression in x, which is the regular language which contains only one element, that's x. Okay, so x is actually in epsilon. So this basically, you can view this basic clause as just a building block for the regular expression. Now, based on this, we can build more, complicated regular expression. So let's say if R and S are regular expression, okay, corresponding to the language LR and LS. Okay, so that means R could be any element in epsilon or in sigma, or R could be an empty string epsilon, or R could be just a phi. So S could be actually in these three actually elements. So then we can build a more complicated regular expression. So if R and S are regular expression corresponding to language LR and LS, LR is R and LS is a regular language which contains the S. Okay. And then we say R plus S, R times S, and R star. These are also regular expressions in the regular language LR union LS. And LR, concatenate LS or LR star. Okay, let's take a look at the first one. So suppose X R is a regular expression of LR. R is a regular expression of LR. Then R plus S basically means it's a regular expression in LR and LS. Now, what is LR and LS? LR is R union S. So two sets, the union of two sets is R and S, right? So R plus S is basically a regular expression in the regular language R and S, which contains R and S. Okay. Now, also, R S is in the language of LR concatenate with LS. So that means it's R and S. Okay. Let's combine the string. So, and also the last case, R star is in LR star, which basically means it's a epsilon R, 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 R. It's just a, star basically means it's concatenate with itself, as many times as you can. So that's basically, so that means if R and S are regular expression, then R plus S, R times S, R star are regular expression in these three different languages. Okay. Now that's the only way we can build a regular expression. And now nothing is regular expression unless it's obtained from the above two clauses. Okay. So this is called a recursive definition. So you can build it from a very simple regular expression to a very complicated expression. Okay. And also the operation star has precedence over the concatenate, which has the precedence over the plus. Okay. So this has a high, precedence, then concatenate, and then plus. So when someone just write a regular expression like this, it basically means this has a high precedence. So C star going to be expressed first, and then concatenate next. So that you have a B next, and then A plus. Okay. So if you put the parentheses over here. So, and also you can use R squared to represent R concatenate with R. And R to the K means R concatenate with R and concatenate with R again. So K times. Okay. So LR is the language corresponding to the regular expression. So now this is kind of a notation we can use. And so here are some of the examples. Okay. So for example, if we just say, what is a regular expression if we write 0 plus 1 square? Okay. So 0 plus 1, you can see that 0 plus 1 is the regular expression in the language 0 and 1, right? So this is actually in the language 0 and 1. Okay. So that means 0 plus 1 is a regular language, regular expression in the regular language 0 and 1. It's a set 0 and 1. Okay. So then once you actually do this under the parentheses, and then 0 plus 1 square is basically corresponding to the language 0, 1, which is actually 0 plus 1, and 0 plus 1 concatenate. So that means, so it is the language which contains one element in the first language, one element in the second language. So you, by the combination, you have 0, 0, 0, 1, and a 1, 0, and a 1, 1. So that's the regular expression in this regular language. Okay, corresponding to this regular language. Okay. Now, what about the 0 plus 1 to the 3? So then it's a concatenate 0, 1, 0, 1, 0, 1. So then you have the language basically contains the string of 1 in the first language, 1 in the second language, 1 in the third language. So you can, by all this combination, you can have a 0, 0, 0, 0, 0, 1, the 0, 1, 0, the 0, 1, 1. So, and then you have a 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay. So 1 plus 0 plus 1 cube is actually corresponding to the language, the regular language of this, which contains all the elements of exactly 3 content. All the elements in this language is the string of length 3. Okay, the string of length 3. 0 star, 1 star. So you can basically do this. First, to check the 0 star. Okay, 0 star basically, which contains, string 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So that's 0 star. Okay, then 1 star is epsilon 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, right? So when you actually concatenate these, then you basically have all the string of 0 before 1. So you can have like a 1, 1, 1, that's fine, because there's no 0 at the beginning. But you're never going to have anything like a 1, 0. So 1, 0 is not in this language, right? Because you always start with 0, any number of 0 plus any number of 1. So just like this. Okay. Now you can actually build another, language using this expression, So a plus b, then star. So that means a plus b star. This gave you a and a b star, right? So then concatenate with a b b. So basically, you're gonna have always has ABB, ABB at the very end. Okay. But before ABB, it could be any combination of A and B. So you can have AB, you can have a AA, you can have a B, A, and then next one you can have a AB, ABA, AAA, ABB, right? AAA or AAB. So anything, but always end with ABB. So because that's defined over here. So let's take a look at another example before we actually move forward. So let's take a look at the last one. What is this? For this regular expression, what is this regular expression belongs to? What is regular language? So AA plus AB plus BA plus BB. That's AA, AB, BA, BB, right? And the star means any actual combinations, any actual kind of combinations. So that's could be epsilon, AA, AB, BA, BB. And the next one is AAAA. Okay, so that means or AAAB, right? Or AABA or AABB, right? So always come with a pair. Okay. So what's next? You can have AB, AA, AB, 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 BA, AB, BB, right? And you have a BA, AA, BA, AB, BA, 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 BB. Then you have a BB, AA, BB, AB, BB, BA, BB, BB. That's all the string with length 4. And the next one going to be all the string of length 6, right? So you always come up with two elements. So then you can always build this. So okay. So the languages look like this. So do you have any questions? So unfortunately for this class, we only actually, provide an introduction for any kind of topics in the math that's related to computer science. Okay. So finite automata is a very, very important math actually knowledge in one of the area called the theory of computation. So typically when you actually try to study any actual math used in the computer, you can think about how the computer going to actually interpret all these strings. So this is actually defined in the theory of computation. So finite automata is just one that they use to define how the machine going to interpret the language, not a human being, but machine. So we have to, the basic idea is to set up a rule, a syntax, or we call the grammar. So we set up a rule and then ask the machine to check based on the rule. So that's basically how the machine gonna interpret any languages. Okay. So so that's basically the topic for the finite automata. If you want to know more about this area, So then I think theory of computation is the course you can take to, get you more in this area. I think that's pretty much all I want to cover for the finite automata. Uh, so the next part we're going to actually talk about is the number theory. Now, number theory it's not actually new area in math. It's kind of a very old math area. But recently, people find a way, they find the application of number theory in many of the computer science area. One of the important area is the computer security, like encryption, decryption. You know, most of the theory built like a cryptography. Uh, it's a one of the branch in math, or exactly one of a branch in number theory. It's not a new area. So people actually 100 years ago they start to actually discuss the cryptography. But now with the modern technology, they find the application of the cryptography. They can use this in the computer or network security. So that's why we want to talk about our next area. That's the number theory. So is there any questions before we continue? Okay, let's start this. So that's module 9, Introduction to Number Theory. And so in module 9, we're going to talk about some of the basic theory in number theory. And then module 10, we're going to talk about some of the application of number theory in the computer security. In particularly, we can talk about some of the topic in cryptography. That's the encryption algorithm. Okay. So here's the number learning objective. So the number theory is a very, very basic. So even in elementary school, you already learn some of the theory about numbers, okay, such as the concept of the divisibility and also the division algorithm. Um, so these are actually not new area. It's actually not really advanced area. It's a very basic area. So number theory is basically talk about numbers. So even elementary school already touched that area. But it's also one of the toughest area in the math research because many of the theories are still very difficult to prove. Okay. So so the one another important area is the prime number in number theory. Okay. The concept is very simple. But when we try to study the prime number, you will find out it is a very difficult area to study. It's very difficult to to find the same kind of you know some of the theory, try to build a some of the theory for the prime numbers. Now, prime number by definition, it's very simple. It is a number that can be divided by only one and itself, right? That's a prime number. However, people try to find out what's the characteristics of these prime numbers. Is there any way I can find a certain pattern so I can predict what is next prime number after this one? Okay, so for example, the smallest prime number is, what is the smallest prime number?
1.
1. Okay. Yeah, you can say 1 is a prime number, but normally people don't count to 1 as a prime number. So they just count to 1 as just 1. Yeah, even though 1, yeah, by definition, looks like a 1 can be divided by 1 or itself, because it is 1, right? But the prime number, normally they view any number, which is bigger than 1, you know, if they cannot be divided by any other numbers, then these are defined as a prime number. Yeah. So normally we think the smallest prime number, we all talk about the positive number. Okay. The smallest prime number is actually 2. 2 is the number, the smallest prime number. Okay. So so we're going to talk about this a little bit later. So when we try to, you know, build a certain of the theory, and we can use these theory in the application of the, encryption algorithm. So divisibility is a very basic concept. So when we talk about an integer, so we say that a non-zero integer b can be divided by, I'm sorry, a non-zero integer b divides a. So that means a can be divided by b, or a is divisible by b, if we can write a as a multiplication of b times something else, multiplication of b by some number m. Okay. So if a can write as the multiplication of two numbers m and b, and then we can say b is a factor of a, and b can divide a. Okay. This is pretty simple, right? So for example, if I can write 6 as 2 times 3, and then we can say 3 divides 6, right? And also 2 divides 6. Why? Because, 6 can be write as 2 times 3. So and the 2 is called a factor of 6, and the 3 is also a factor of 6. Okay, so 2 divides 3 and 3 divides 3. Okay. Also, any number you can write as its factor also times 1. So 1, so that's why in many cases people are going to actually ignore the number 1, because anything multiplied by 1 is just itself. So it doesn't really make any change, make any difference. So you can say 3, or you can say 3 times 1. It basically 3 times 1 is the same as 3. So normally, by, if you multiply 1, it doesn't make any change. So that's why we normally ignore the number 1. So 6. So when we say what is the factor of 6, factors of 6, you can say 2 and 3. But also you can include 1. 1 is always the factor of any numbers, integers. Okay. So 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 basically when we say b divides a, that means b can divide a, and there's no remainder on division. Okay. Now when we say, so for example, b equals 3, if a equals 6, then we b divides 6. 3 divides 6, because when we divide 6 by 3, and you can put the 2 as the quotient. 2 times 3 is 6, and then you get a remainder, which is 0. And in this case, we say b divides a. So 3 divides 6. Now b divides a. 3 divides 6. Now, if b is 3, a is 7. So if we try to do the elementary division, we can 7 divided by 3. Then you can put the quotient to 2. 2 times 3 is 6. 7 divided 7, subtract 6 minus 6 is 1. And then 1 is smaller than 6, so you cannot do any division anymore. So this is called remainder. Okay, so the remainder is 1. So 7 divided by 3, you got a quotient of 2 and the remainder 1. In another word, we can write this. We can write 7 as 3 times the quotient. 3 times the quotient plus the remainder. Okay, so you can say it's 3 divided by 7, then you got a quotient 2 and the remainder 1. Okay, now b divides a, so that means 3 cannot divide 7, but 3 divides 6, because 3, when you divide 3, when you divide 6 by 3, you got a remainder 0. But in this case, the remainder is not a 0. So that means 3 does not divide 7. Okay. So normally, if b divides a, we actually use the notation that the b, we put the bar a, so that means b divides a. Okay. So when b divides a, we say b is a divisor of a. Okay. So basically you can use several different terminology, but basically they means the same thing. So when I say b is a divisor of a, or b is a factor of a, basically it means the same thing. So 2 is a divisor of 6, or 2 is a factor of 6. They basically means the same thing. Okay. So for a positive divisors of 24, what are the positive divisor of 24? So every number that can divide 24, right? So 1 can divide 24, 2 can divide 24, 3 can divide 24, 4 can divide. All these numbers can divide 24, including 24 itself. Okay, so these are all the divisors of 24. And also 13 divides 182, because you divided 182 by 13, you got a remainder 0. Minus 5 divides 30. 17 divides 289. And the minus 3 divides 33. 17 divides 0. 0 is also a special number, just like a number 1. Also 1. 1 is a special number, but 0 is also a special number. 0 can be divided by any number. 0 can be divided by any number. So 17 divides 0. 2 divides 0. 3 divides 0. So 0 can be divided by any number. Okay. So that's the concept of divisibility. And here are the properties of divisibility. Okay. If A divides 1, A divides 1, what does that mean? So I can write 1 as A times any number, right? Because A divides 1. So that means A can divide 1. Okay. So A can divide 1. That means 1 can be written as A times some number. So in that case, in this case, A has to be either 1 or -1. And also M must be 1 or -1. Because you cannot split 1 into a smaller factor, you know. So if A divides B and B divides A, then A and B are technically has the same value, except that you have a positive or minus sign. Okay. So like a 3 divides 6, but 6 cannot divide 3 because you cannot write 6 as 3 as 6 times any number, right? So that number cannot, there's no such an integer that the 6 times that integer equals 3 because 6 is bigger than 3. So you cannot do this. So, but 6 can divide 3, a 3 can divide 3, and a 3 can divide 3. So that means, and yeah, you can switch the order. So technically, you can easily prove this. If A divides B, what does that mean? So A is a factor of B, right? So I can write B as A times some number M. Okay. So A divides B, that means B can write as A times something because A must be a factor of B. Now if B divides A, so that means A can be write as B must be a factor of A, so I can write A as B times another number N. Okay. Now if A divides B and B divides A, that means both of this is true. Now what does that mean? So that means I can write B equals A times M, and A is B times N. So so B times N and M. Okay. So B equals A times M, and I replace A with B and N. So now you have B equals B times N and M. So that means B N times M must be 1, right? Has to be 1. Okay. So if N times M has to be 1, so that means N divides 1. M divides 1, right? Now if anything divides 1, that means N equals plus or minus 1. M equals plus or minus 1. So that means B equals plus or minus A because both N and M. So that means B equals plus or minus A. So, or on another hand, A equals B plus or minus B. It basically means the same thing, you know. So that they are technically of the same size. Okay. So any number B divides 0. Okay. Because 0 can be written as B times 0. So B divides 0. Okay. Now, if A divides B, B divides C, then A divides C. That's also easy to prove. Okay. I'm going to leave that to you. Okay, how can you prove this? Now, if B divides G, B divides H. So B can divide G, B can divide H, and then B can divide M times G plus N times H. Okay. That sounds very straightforward, right? Because if you use the number, looks like it will be actually easy to do this, you know. So if B actually divides G, So that means G can write as B times some number, right? And if B divides H, that means H can write as B times some number. Okay. Oh, I'm not going to use M because M is actually used here. So G can times equals B times some number. I call it times T, some number T. B times as H, then H can be written as B times some number S. Okay. So then M G plus N H equals G is B M B T plus N times BS. Okay, so that means if I take the common factor B out, so it's MT plus NS. So what does that mean? So that means MG plus NH has a factor or divisor B, right? B is a factor of this. So B divides this number. Okay, so B divides this number. Okay, because B is a factor of this number. So now these are very basic properties of the divisibility. Now I'm going to slow down, give you more time to absorb this. Do you have any questions on this? Because if you don't, then I'm going to move forward. No? Okay. So now let's actually build some algorithm, the division algorithm. Okay. Now let's give it a positive integer n, a positive integer, and any non-negative integer a. Okay. So if a, we divide a by n. So if we divide a by n, so we get an integer q, which is a q quotient of the division. And also another integer called the remainder that basically obey the following relationship. So we divide a by n. So a is divided by n. Okay. So if you actually try to draw this, illustrate this using the diagram, we can think about this. Suppose this is actually a line. Okay. A line may have value, right? So a is over here. A is over here. So that's the size of a. Okay. Now, if we divide a by n, so that means, think about this. A is the length, okay? Okay, so for example, a is a sticker of certain length, okay? So this is the length of a. Now we want to divide actually that sticker into a smaller fragment. Now each fragment size is n. So a we divide a by n. That means we cut the a into a smaller piece. Each piece is a size n. So we cut so here's the a, and the n is smaller smaller than a. So we cut the one piece. That's n. So if we start from 0, and that's n, right? And then we cut another piece of n. So then here's n. We cut another n. So we got 2n. And we cut another n. We got 3n. And we cut another n. We got a 4n. So we keep cutting this n. And until we cut up to like qn. And then that's the q is the number of fragment we actually just cut. We keep cut. And then qn, it's still smaller than n. So, but if the value qn and a, between qn and a, is smaller than n, now that value is called a remainder. Okay, and then we call it r. So that's a remainder r. So this is basically the idea for the division. So if we say, if a is this line, this big, and then we divide a by n. So if we got a quotient of q, so that means there's a q segment of n, and then until we reach the point that there's no actually fragment of n remaining, and then that's the remainder. Okay. So one of the example is like if a is 70, okay, and we try to divide a divided by 15. So 70. So we cut the 70 into a length of 15. So that's a division. 15. So we got a 30, 15. We got a 45, and a 15. We got a 60. 0 to 15, 15, 30, 30 to 45, 60. And the 60 to 70, okay. Now, that's smaller than 15, right? So we cannot cut anymore. So that smaller, and the difference, the length of this is 70 divided by, subtract the 60, that's 10. So that's a remainder, okay. So the remainder is 10. So that basically means, when a is 70, when a equals 70, so we can write 70 in terms of the value 15 times how many, the quotient, which is 4, right? Plus the remainder. So 70 divided by 15, you got a quotient of 4. That means that's the number of 15 segments, and plus the remainder 10. Okay. Now, if the number a is 60, and if we try to divide 60 by 15, then what's the remainder? So 60 divided by 15, so you have a 15, 15, 15, 15, and you exactly reach 60, right? So the remainder is 0. So in that case, 60 actually divided by 15, you got remainder 0. So 15 is a factor of 60, or 15 is a divisor of 60. You can say that. So that's basically interpretation of division. So basically you have a sticker which of certain length, and then you try to divide this sticker into smaller pieces, and if there's exact match, the remainder is 0. So that's perfect. You can exactly cut this length in this sticker into a smaller size. But if you cannot exactly match, then the last piece is going to be a very short piece. That's a remainder. Okay. And the number of smaller pieces is called the quotient. Okay. So we can always write this. If A divided by Q or by N, then you have a quotient Q and the remainder R. Okay, I is always between 0 and N. I should be less than N. If I is bigger than N, that means you can cut another piece, right? So you can actually still keep a smaller. So R should be. That's the reason why it's called a remainder. It's always smaller than N. Okay. Now sometimes we use A divided by N, and then we use this just basically means it's a floor division. So that means we divide A by N, but we only keep the integer part. We threw away the fractional part. One of the basic techniques of number theory is called the Euclidean algorithm. Okay, the Euclidean algorithm is used to determine the greatest common divisor of two positive integers. Okay, sometimes we try to find out whether this number is a divisor of the other number, right? So we can do the division to see whether the remainder is 0. If the remainder is 0, then the number is the divisor of the other number. If the number is not a 0, and you got a quotient, you got a remainder, so it's not complete. You cannot exactly divide the number. So suppose I have two numbers, two positive numbers. Okay. Now, for two positive numbers, one of the actual problem people try to figure out is, can I find a common divisor? So that means I have two numbers, two positive integers. So is there any way I can find a divisor which can divide both the number A and the number B? Can I? Anyone can provide the answers for this? Okay. Oh, I find two messages here. Some messages here. Let me just check the message here. Oh, okay. Can the class be recorded? Yes, I'm doing that now. So, for example, let me give you an example. If I have two numbers, 24, and another number, let's say 16. Can I find a common divisor? So that means a number that can divide both 24 and 16.
2, 4, 8.
Okay, so I can find a 2, right? 2 can divide 24. 2 also can divide 16 because 2 is the factor of 24 and the 2 is a factor of 16. What is the number? 8 to 4, right? Because 4 can divide 24, 4 can divide 16, and also 8. So I can find not just one common divisor. I can find multiple common divisors. I can find more than one common divisors. Is that correct? Any other numbers? Of course, 1 is always the common divisor, right? Don't forget 1. 1 is always the common divisor. Yeah. Anything else? Looks like that's it, right? Now, in general, how can we find any common divisors? For example, if I give you another example, like a 36, 24. Now you can figure out how can I find a common divisor. Now, one of the way you can do this is to factor each of the number, right? Can I factor the number?
Yes.
You have a 2, 3, 2 times 3. Actually, 2 times 2 times 3 times 3, right? Now, if you want, I can also add a 1. For 24, I can say 2 times 2 times 3 is that right? Okay.
And multiply 2.
Okay. And that's actually times, right? And also times 1. Okay. So that's 2, 2, 2. So these are all, each of these are a prime number. Okay. So that's probably the smallest number I can just factor. Now, if we try to find a common factor, and then it's probably relatively easy to find a common factor, right? Common divisor. Okay. So it looks like both number has 2, right? Okay. And both has 2 times 2, so it's 4. And both has 2 times 3, 6. Both has 1. 2 times 2, 2 times 2, yeah. 2 times 3, 2 times 3, yes. Here you have a 3 times 3, 9, but 9 is not the factor of, not the divisor of 24, right? Oh, you have a 2 times 2 times 2 times 3. Okay, 2 times 2 times 2 times 3. So 2, 2, 3, 2, 2, 3. So you have a 12. So it looks like the 1, 2, 4, 6, 12. These are the common divisor, right? Okay. That's cool. So we actually find it. So we need to do the factors. You can factor each of the numbers, and then you find the common numbers, the combination of common numbers. Okay. Now this is actually called the common divisors of two positive integers. Now, in some case, so if I give you two numbers, like so that's the example. Another case is like if I give you the number like 15, and the other number is, for example, 16. So if we try to find a common divisor, okay, do you think we can find a common divisor?
There's only one.
Okay. Of course, 1 is always the common divisor. 1 can divide any numbers. Okay. But other than 1, you cannot find anything else, because if you factor 15, 15 can be written as 3 times 5 times 1. And the 16 can be write as 2 times 2 times 2 times 2 times 1. So you have a 2, 2, 2, 2. So now if you look at this, the only common factor is 1. So there's nothing in common other than 1, right? So in that case, the only common divisor is 1. Okay. Now, in that case, we call these two numbers relatively prime if their only common positive integer vector is 1. So 15 and 16 are relatively prime. Okay. So each number is not a prime. 15 is not a prime number, right? Because you can factor 15. So 15 can be divided by 3 and 5, which is not a prime number. 16, of course, 16 is not a prime number. It's actually even number. Okay. But 15 and 16, these two numbers are relatively prime because they don't have any common factor. Remember, that's a very important property in the number theory. So we're going to actually discuss this later. Now, one of the important common factor is something called the greatest common divisor. It's a greatest common divisor. Now you can list all the divisors, the common divisors. And then what is the greatest common divisor? The largest one is the greatest common divisor. So 8 is the greatest common divisor between 24 and 16. Now, what is the greatest common divisor between 36 and 24? 12, right? Now, what is the greatest common divisor between 15 and 16? There's only one divisor, right? That's a 1. So 1 is also regarded as the greatest common divisor. Okay. In another word, if two integers are relatively prime, it means the greatest common divisor between these two numbers is 0. Oh, I'm sorry, is 1. If the greatest common divisor is 1 between two numbers, that means these two numbers are relatively prime. Does that make sense? I'm gonna move forward. Okay. So the greatest common divisor of two numbers A and B is the largest integer that divides both A and B. We know that, right? Okay. So we can use the notation GCD of A and B. So in another word, GCD of 24 and 16 is 24 and 16 is 8, right? GCD 24 and 36 is 12, right? Now, what is the greatest common divisor for two numbers? Like if the two numbers are 0. Now that's very tricky. Okay. So for 0 and 0, can you find out the common divisors for 0 and 0? If two numbers are 0, both are 0. Do you think, is there any common divisor? Can I hear anything?
Can we say 0?
Yeah, 0 is a common divisor. Yes. 0 is a common divisor for 0. 0 is a divisor of 0 because you can write 0 as 0 times any number. So 0 is a divisor of 0. 0 is a divisor of 0. Okay. Okay. But can we find any common divisors? Technically, any number, any integer number is a common divisor. Because 5 can divide 0. Right? If you divide actually 0 by 5, you can get a quotient to 0, and 0 times 5 is 0, 0. So you can, so 0 can be written as 5 times 0 plus 0. So 5 is a divisor of 0 because you can write 0 as 5 times 0. Okay, so 5 is a divisor of 0. So any number can divide 0. Any number can divide 0. That sounds very strange, right? This is very strange. Because let's go back. Any number, any b, if b is not 0, divides 0. Okay, any number divides 0. Because 0 can be written as b times 0. So b is a factor of 0. So any number can divide 0. So in that case, if we talk about the greatest common divisor between 0 and 0, doesn't make any sense. However, in math, we have to define the greatest common divisor between 0 and 0 is 0. That's the definition. It's not because the greatest common divisor between 0 and 0 is 0, but we define it as 0 because otherwise it doesn't make any sense. Any number could be a divisor, could be a common divisor. So what do you think? You think 100 is the greatest common divisor? No, because 101 can divide both. And you can think about 102 is a common divisor. No, 103 is also a common divisor. So there's no limit. Okay. If you think of what's the greatest common divisor, the greatest common divisor is infinity. It's really, you cannot find a largest one. There's always a larger one. So that's the reason why in math, we just say there's uncertainty. So we have to define the greatest common divisor between 0 and 0 is a 0. Okay. So by definition. Okay. So here's the property for the greatest for the greatest for any number. So a positive integer c is said to be the greatest common divisor of a and b. Okay. C is the greatest common divisor of a and b if C is the divisor of A and B, of course, right? First, the greatest common divisor is a common divisor first, right? A common divisor may not be a greatest common divisor because, like in this case, a greatest common divisor is a common divisor for 24 and 16. But a common divisor may not be a greatest common divisor. 2 is a common divisor. 4 is a common divisor, right? But they are not greatest common divisor. So the other way is true. The greatest common divisor is a divisor of A and B. Another condition, if a divisor of A and B is a divisor of C, that's a little bit tricky statement. Okay. So this also says, any number, let's say b, a t. Okay, if t can divide a and t can divide, if t can divide a, and t can divide b, and then t also going to divide c. Now, if these two conditions true, then c is the greatest common divisor. Now, if you go back, you can find out this is always true. Now, 8 is the greatest common divisor, right? So that means 8 is a common divisor. So 8 divides 24 and 16. Now, the second condition says, if any other number can divide both, like a 2 divides 24 and that divides 16, 2 can also divide 8. 4 can divide 24, and 4 can divide 16, and 4 can also divide 8. So any common divisor of 24 and 16 is also a divisor of the greatest common divisor. Okay. So any divisor of 24 and 16 can also divide 8, the greatest common divisor. So this is actually not an accident. So you can say 2 can divide both, but 2 also divides 12. 4 can divide 12. 6 can divide 12. So the greatest common divisor can be divided by any of the common divisors. Okay. So that's basically what this says. So we can define this. The greatest common divisor of A and B is any k that can divide A and B, but the largest of such a k. Okay. So the largest common divisor is the greatest common divisor. Now, in many times in math, if you are given two numbers, we're not looking for all the common divisors. We are only looking for the greatest common divisor, the largest common divisor. Okay. Okay. So here are some more properties. Okay. So now, typically, when we talk about the greatest common divisor of A and B, I always assume A and B are positives. It does not mean that this concept does not apply to a negative number, but we find out, if we put a negative sign on any of the number, it doesn't change the result. So the greatest common divisor between A and B is the same as the greatest common divisor between A and minus B. And it's the same of greatest common divisor between minus A and B, or it's the same as greatest common divisor between minus A and minus B. So in that case, if we try to talk about what is the greatest common divisor between minus 16 and 24, then in that case, to reduce the confusion, we just say, okay, forget about the minus sign. We just think about 16 and 24, because the greatest common divisor of 16 and 24 is the same as the greatest common divisor between minus 16 and 24. It's the same. So we typically gonna ignore any negative number. So when we talk about the greatest common divisor, we only talk about a positive number. For a negative number, it's fine. We can get rid of the negative sign. Okay, and the result still hold. And then we also talk about the greatest common divisor of A and 0, and it's always the absolute value of A. Okay, so the greatest common divisor of minus 36 and 0, and it's the same as greatest common divisor of 36 and 0. So it's 36. Okay. So that's always the case. And also we notice that if two numbers, integers a and b, are relative prime, then it's the same as saying the greatest common divisor between these two numbers is 1. So that means if and only if a and b are relatively prime. So if they are relatively prime, then it's the same as saying the greatest common divisor between these two numbers is 1. Now we're going to use this in our next module when we talk about the security, when we talk about encryption algorithm. Now, next thing we're going to talk about is, let's say, if you're given two numbers, how can I find out the greatest common divisor? Now we can say, okay, I can do this, right? We can just factor each of the numbers. We can factor each of the numbers, and then we find the greatest common divisor, the largest common divisor. That's the greatest common divisor. Yeah, we can do that. But you realize it's very costly. Factoring a number is really a costly job. So normally people try not to do that. And there's one algorithm. It's called the Euclidean algorithm. Okay. It's basically developed by the mathematician called Euler. The Euclidean algorithm basically says the greatest common divisor between A and B is the same as the greatest common divisor between B and A modulo B. Now, what is A modulo B? So A modulo B is, when you divide A by B, you got the remainder, and the remainder is the result of A modulo B. Okay. I'm gonna actually hold it for a while, and I'm waiting for any questions. Do you have any questions? I'm not gonna prove this, but I will actually work on certain examples. Okay. So the Euclidean algorithm will easily give you the solution for the greatest common divisor without factoring each of the numbers. Okay, without factoring each of the numbers. Now, if you write an algorithm using any computer language, here's the algorithm. The algorithm you can use is pretty simple. It's basically, this is called recursive algorithm. So you define a method. A and B are two integers. You define a method called Euclid. And then you actually call this method with two numbers. Okay. So we're going to talk a little bit more about modular operation. Okay, A mod B. That's called a modular operation. But right now, you just need to know A modular B is the remainder when you divide A by B. So for example, let's say, what is the A 16 modular 7?
2.
Okay, 2. You say 2, right? Let's check. So you divide the 16 by 7. Okay, so then what are you going to put here? Quotient is 2. 2 times 7, that's 14. And you got to remainder 16, minus 14, that's 2. Yes. So the remainder is 2. So this is 2. Okay. Now 17 modular 3.
2.
Oh, also 2. That's interesting. Let's say 75 modulo 8. What is that? You can put a 9. 8 times 9 is 72. 75 minus 72, that's 3. So the remainder is 3, right? Now, it doesn't matter how big the number going to be. So let's say 973 modular 23. Okay. What is the result? Okay. Let's actually take a break, small break. And when I come back, I hope that you already find the answer for this. 973 modular 23. What is the answer? Okay. Let me first stop the recording.